Hi everyone, thank you for joining us. I'm Trish McLean, the marketing person at Mirus, and we're happy to have people today from all over the world joining us for the webinar, How Harmonics Have Led to 6 Power Factor Misconceptions. Our presenter today is Tony Huvenar. He is the president and CEO of Mirus International and a professional engineer. Tony joined Mirus in 1996, having previously held the position of Chief Facilities Electrical Engineer at IBM. Tony has over 30 years' experience dealing with the issues caused by harmonics, and he has gained valuable insight in the resolution of power quality related problems. He has published and presented numerous technical papers on power quality and harmonics, and we're very happy to have him with us today. A few logistics for today's webinar. Because we have over 90 people on the line, everyone's sound is muted. Please send your questions in via the console question section. We will answer questions at the end of the presentation. The presentation itself will be about 30 minutes with questions to follow. And for those of you who require documentation to apply for professional development hours, please note that we'll be sending attendees a certificate of participation and a test following the webinar. And with that, I'll hand it over to Tony.
Thank you very much, Trish, and good day, everyone. I'm extremely pleased that so many of you have been able to join us today for this webinar on power factor misconceptions. Hopefully we found a time slot that was convenient for each of you, although this is quite difficult to do with participants from all corners of the globe. I'm sure it is the middle of the night for at least some of you. Mirus has been assisting customers with treatment for harmonics since our inception in 1991. And with this experience, we have found there to be a general misunderstanding on how power factor is affected by harmonics. So I decided to write a white paper on the 6 most common misconceptions. The white paper is available for download from our website, and the webinar today will provide further insight on this topic. Although a low power factor does indicate that a power system is not being effectively utilized, if this occurs only when the system is lightly loaded and the reactive power component in kVAR is quite low, there is no need for concern. Only when the power factor is quite low under more heavily loaded conditions does it need to be addressed. Placing conditions that are too rigid with respect to power factor can lead to installations that are more complex, costly, and unreliable than necessary. And in many instances, a little leading power factor can be effective in compensating for inductive reactive power located elsewhere on the power distribution system. Today we'll be discussing power factor and the power triangle, the 6 misconceptions of power factor, nonlinear loads and the harmonics they generate and their impact on power factor, utility power factor penalties, power factor correction capacitors and the potential for resonance with the power system, passive harmonic filters and their relationship to power factor at various load levels, and the effect of leading power factor and capacitive reactance on generators. For those trained in electrical theory, the concept of power factor used to be fairly simple to understand. Power factor is a measure of how effectively a specific load consumes electricity to produce work. It is the ratio of real power in kilowatts to apparent power in kVA. The higher the power factor, the more work produced for a given voltage and current. The power factor triangle, shown on this slide, applies only to linear loads, however, and it is often referred to as displacement power factor, or DPF. The inductive component or capacitive component of reactive power is shown on the y-axis, inductive being upward and capacitive being downward typically. And then we have the real power in kilowatts on the y-axis. And the sum of these two vectors results in the apparent power in kVA. And there is an angle theta between the apparent power and the real power. Power factor is equal to real power divided by apparent power, or kilowatts divided by kVA, and is equal to the cosine of that angle theta. Apparent power is the square root of real power squared plus reactive power squared. kVA equals the square root of kilowatts squared plus kVAR squared. So the first power factor misconception is that low power factor is normally caused by electric motors and other inductive loads. Although it is true that inductive loads consume reactive power and thereby reduce power factor, with today's proliferation of harmonic generating power electronic nonlinear loads, low power factor is now most often due to harmonics. Second misconception is that low power factor can always be corrected by adding capacitance. If low power factor is due to harmonics, treating with capacitors can often make the problem worse. Third is power factor must always remain high to prevent power factor penalties. In reality, although there are many different ways that power factor penalties are applied by utilities throughout the world, they almost universally apply these penalties during periods of peak demand. Therefore, if low power factor only occurs under lightly loaded conditions, it will not result in power factor penalties. The fourth is that harmonic filters must always be equipped with contactors to switch out capacitors under light loading conditions. In reality, many harmonic filters do require switching out contactors under light loading conditions, but not all. So a properly designed harmonic filter will not require switching out of capacitors. The fifth is that leading power factor is a problem for generators under any condition. It is true that a leading power factor that results in high levels of capacitive reactive power is a problem for synchronous generators, but in certain conditions, power factor can be low and leading without there being too much capacitive reactive power for the generator. And finally, the simple statement that any leading power factor is bad. A leading power factor can be useful in compensating for a low lagging power factor, as long as we ensure that the capacitive reactive power is not too high. Therefore, it is not always a bad thing. So when we have nonlinear loads, the harmonics that they generate affect power factor. Typical nonlinear loads are rectifiers such as a variable speed drive. And these don't typically shift the current, but rather distort it. Harmonic currents that are generated do no useful work and therefore contribute to reactive power. The power vector relationship then becomes three-dimensional. This graph we show that the reactive power, we still have the reactive power in inductive or capacitive. We now have a distortion harmonic component, and we have the real power in kilowatts. The distortion harmonic component is 90 degrees out of phase with the inductive or capacitive component and 90 degrees out of phase with the real work. The apparent power now in kVA is the vector sum of all three. So we've got the real power, the inductive or capacitive power, and the distortion reactive power to result in the full apparent power to be delivered. Power factor is still real power over apparent power, or kilowatts over kVA, but it no longer equals cos theta. Cos theta is still referred to as displacement power factor. Apparent power, S, equals the square root of real power squared plus the inductive or capacitive component, Q squared, plus the distortion component squared. Or kVA equals the square root of kilowatts squared plus kVAR squared, inductive or capacitive, plus kVAR squared in distortion. So true power factor now is equal to displacement power factor, dPF, times the distortion power, HPF. And this is not a new discovery. The reference shown here at the bottom of the slide is actually taken from a text that was published in 1939. In this slide, I used to show the relationships between harmonics and power factor. So the first column is our harmonic number, starting with fundamental being 1, and then we have the odd orders up to 21. Second column shows the percent fundamental, the percent of fundamental for each harmonic. So the fundamental current 1 is 100%. Third harmonic here is 70% of the fundamental. Fifth harmonic is 35%. The next column I show percent RMS. Percent RMS is often the way harmonics are described, or total harmonic distortion is described in Europe and other areas of the world. Here the harmonic numbers are referenced with respect to the total RMS value. So third now is 54% of the total RMS value and still is 70% of the fundamental. The last column shows an I squared H squared relationship. This is what is used to determine K factor. K factor is a measure of essentially a measure of the additional losses and heating associated with harmonics in a transformer. And we use K factor values to define how well a transformer is going to be able to handle a specific harmonic load. So total harmonic distortion is equal to, it's a root sum square calculation, so it's equal to the square root of each harmonic squared. So we have a second order squared plus the third order squared and so on. Take the square root and divide by the fundamental component. So in this example, the particular spectrum has a total harmonic current distortion of 83%. K factor is the sum of all the I squared H squared H squared products. And so we take each of those, we sum them all up, and in this particular example, K factor is 9. So this particular load profile would require a K factor 9 transformer in order for it to be fully loaded. And finally, distortion power factor is defined as 1 over the square root of 1 plus the total harmonic current distortion squared. So when we do that calculation in this example, the power factor is 0.77. So this particular load profile has a total harmonic current distortion of 83%, a K factor rating of 9, and a power factor of 0.77. This next slide shows typical nonlinear loads, so variable speed drive loads. The first row shows a 6-pulse rectifier, PWM VSD, and it shows the typical double pulsed waveform of the current. The harmonic spectrum of the current, which is predominantly 5th and 7th, but also contains 11th and 13th, and so on. Total harmonic current distortion of this particular load is almost 73%, and the power factor is 0.79. If we add a 3% AC line reactor to the input of that VFD, it broadens the current waveform a little bit, thereby reducing the harmonic content. So you can see that in the spectrum. Total harmonic current distortion then is reduced to 36, or almost cut in half essentially, and the power factor improves by the removal of these harmonics. 12-pulse VFD, which uses a phase shifting transformer on the input to get cancellation of certain harmonics, predominantly the 5th and 7th, is shown in the next row. We have residual harmonics of 5th and 7th, we have 11th and 13th. Total harmonic current distortion now is just under 10%, and power factor is improved to 0.98. The final row shows the effect of a lineator being applied to the 6-pulse rectifier in the first row. We now have an almost sinusoidal current waveform. The current harmonics are virtually eliminated. Current distortion is dropped to less than 6%, and power factor now is near unity. So the first misconception on power factor is that low power factor is normally caused by electric motors and other inductive loads. Whereas in reality, low power factor is most often caused by distortion, reactive power, introduced by harmonic generating power electronic nonlinear loads. Now most utilities, and I know not all locations utilities apply power factor penalties, But most utilities charge their customers for energy supplied in kilowatt hours during the billing period plus a demand charge for that period. And the demand typically equals the peak kilowatts load during a set period. Often that's 15 minutes, but it can be longer. Some cases it's 30 minutes or so. But there's a set period where they'll measure the peak demand load and charge you based on that. If power factor is lower than required by the utility, often 0.9 or 0.95, then the utility may also apply a power factor penalty. And an example of this would be if the utility had a 0.9 power factor as their minimum allowed power factor, then if the peak demand happened to be 800 kilowatts, but the active power component was 1,000 kVA, or apparent power is 1,000 kVA, then our power factor, this would indicate a power factor of 0.8. The utility would charge the customers if the demand were 0.9 times 1,000 kVA, so the power factor being 0.9, which would be 900 kilowatts, which it would result in a penalty of 100 kilowatts. So if the demand charge was, say, $10 a kilowatt hour per month, that penalty would be $1,000 per month. So these penalties can be quite severe depending on how low the power factor is and what level the utility's minimum power factor is applied. So if we improve the power factor in this application to 0.85 and we maintain the same load at 800 kilowatts, this would lower the penalty to just 47 kilowatts, or $470. Because essentially 800 kilowatts divided by the power factor of 0.85 is 941 kVA, and a 0.9 times 941 kVA is 847 kilowatts. So the difference between the actual real power of 800 and the penalty is 847 minus 800, or 47 kilowatts. For power factors that are 0.9 or unity, there would be no power factor penalty. And it is important to note that if the low power factor appears only under lightly loaded conditions, it will not affect the demand charge. This is because demand, by definition, is only at the heavy loading conditions. So if we do not need to have particularly low power factors or particularly high power factors at lighter loads. So misconception number 2 is power factor must always remain high to prevent power factor penalties. And the reality is that power factor penalties are only applied at times of peak demand. Therefore, low power factors during light loading conditions will have no consequence. So we typically will address a low power factor by applying power factor correction capacitors. But this is effective only with respect to displacement power factor. So our power triangle shown here, we have a power factor of 0.8, which has a real power factor of 800 kilowatts. Our inductive power factor is 600 kilowatts. And the apparent power, so sum of the two vectors, ends up being 1,000 kVA. So if we need to improve the power factor to, say, 0.93 to meet the utility's minimum requirements of 0.9, then applying the apparent power equation, S equals P over PF, the power factor, we get 800 divided by 0.93. We need to have 860 kVA. Since Q equals the square root of the apparent power minus the real power, then you can substitute those into the equation, and you find that you need 315 kVAR of capacitive reactance in order to compensate for the inductive component to get the total, you need a total kVAR or reactive power of 315, which, when you subtract from the inductive power component of 600, results in a capacitive reactive power requirement of 285 kVAR. So that's a fairly simple calculation when we're dealing with purely linear loads. But we have misapplications of power factor correction capacitors. PFC capacitors can be beneficial when power factor is low due to inductive loads, such as fixed speed motors, but they can make matters worse when the low power factor is due to distortion reactive power introduced by nonlinear loads. So when Q is low but H is high, PFC capacitors will provide minimal improvement. Power factor must be improved by applying harmonic mitigation equipment. So in this three-dimensional diagram here, we show a very small component of inductive reactive power, but a much larger component of distortion reactive power, and the vector sum results in a high level of kVA. Misapplication of power factor correction capacitors can lead to overcompensation and resonance with the power system, because applying power factor correction capacitors to improve this power factor will not reduce the power factor very much. And what can happen is we can introduce a system harmonic resonance condition. Here we have the source and its reactive, so a simple one line that shows the source and its reactance. A nonlinear load, which might be a variable speed drive, fed from a transformer, and that transformer has a reactance component. And then power factor correction capacitors connected in parallel to the bus, and other loads on the system, which here we're representing as fixed speed motors or induction motors. The equivalent diagram of that simple one line is shown to the right. And here we've got harmonic current source injecting harmonics into the power system. These harmonic currents pass through the source impedance, the transformer impedance. And then they pass through the combination of the parallel capacitance and the inductance of the system. And the inductance of the system is also a parallel combination of the loads, the other loads, and the power system reactance. Resonance will occur where the inductive graph line crosses the capacitive line. And at this point, our resonance frequency is going to be 1 over 2 pi root LC. If that particular resonance frequency happens to be at a harmonic that is common on the power system, is generated by our nonlinear loads, then we can create conditions where we'll get a lot of circulating current between the power factor correction capacitors and the other loads in the system. The circulating current will produce more voltage drop across here, and that voltage drop appears as a harmonic voltage that will drive more current through the system, and it'll continue to increase, basically limited by the resistance in the system. And so the result can be very high levels of current and voltage distortion. These high level of currents and voltage distortion can destroy the capacitors and the fuses protecting those capacitors. Can damage surge suppression equipment. It can cause failure of connected equipment on the bus because your bus voltage gets badly distorted, and thereby can result in system shutdowns. So resonance is definitely a condition that we want to avoid. And I'd just like to provide an example of where a power system resonance occurred. And the utility and the customer, the utility's customer, weren't aware of it until after it had caused a lot of problems on their system. This is an oil field in Midwest USA where that was equipped with a lot of electrical submersible pumps, or ESPs. And these the utility saw that the power factor was low and forced the oil company to install power factor correction capacitors in an attempt to improve the power factor. When Mirus was brought on board, it was after the utility noticed that the distortion levels, both voltage and current distortion levels, were high, and they then forced the oil company to install harmonic mitigation equipment. But as we were analyzing the situation, we could see that the voltage distortion levels, which are shown here with there were two sets of cap banks on the power factor correction system. The voltage distortion levels were over 14%, which were extremely high. And we've seen high voltage distortion levels, but that was much higher than we would anticipate in this kind of a system. And there were high current distortion levels that were driving that voltage distortion. But we believe that there was some resonance on the system, and so we requested that the utility switch off the capacitors and take measurements as they were switching off the capacitors. So when they took one capacitor bank off, you can actually see the power factor actually increased slightly rather than dropping. And this was the result of the voltage distortion dropped as well, because we essentially were removing part of the resonance in that system. When they turned all the capacitor banks off, both sets, the voltage distortion dropped to between 8 and 9%. So still high, relatively speaking, because IEEE 519 requires that voltage distortion levels remain below 5%, so it was still above that and still required harmonic mitigation. But we were starting at a much lower level than at the 14%. So by removing the power factor correction capacitors, we eliminated the power system resonance, and then by adding harmonic filters to the electrical submersible pumps, we were able to improve the power system voltage distortion to much less than 5%. So misconception number 3 is that low power factor can always be corrected by adding capacitance. In reality, if low power factor is due to distortion reactive power, adding power factor correction capacitors will not only be of minimal benefit, they may very likely make the harmonic problem worse by resonating with the power system impedance. So let's take a second and look at passive harmonic filters and power factor. So if we have high levels of distortion reactive power, then the only way to improve the power factor is to remove the harmonics. And one method of doing that is through passive harmonic filters. Having a properly designed harmonic filter, however, is critical to ensuring that harmonic mitigation meets the targeted levels without introducing excessive capacitive reactance under lightly loaded conditions. The large capacitor banks of conventional trap filters and most broadband filters present a high capacitive reactance to the power system, which can raise voltages or cause excitation control problems in generators. Mirus offers Lineator, which is a passive harmonic filter. It is applied to the input of variable speed drives and treats the entire spectrum of harmonics generated by these drives. We can get better than 18 pulse performance when applied to a simple 6-pulse VFD. We'll meet the IEEE 519 harmonic limits of less than 8% total demand distortion at the input to the filters, and that will reduce the contribution of these VFDs to the overall distortion of the bus, ensuring less than 5% voltage distortion. We also have models now available with less than 5% TDD if this is a requirement for a particular application. By removing the harmonic content, we restore the power factor to near unity. We do this using a capacitor bank that is designed to keep the capacitive reactance less than 15% of the rated kVA of the filter. And this is how we can ensure compatibility with generators. And I'll talk a little bit more about that going forward. We have extremely high efficiency, so the highest efficiency of all filters in the market, and higher efficiencies of other forms of treatment, such as transformers used for phase shifting, for multi-pulse systems, or active front-end drives, or parallel active filters. The key is in the design of our reactor. It's a very unique reactor, which allows us to keep the capacitor bank small and get the high level of performance. And there are sizes up to 3,500 horsepower available. So this slide shows the basic connection diagram for a filter. There is an input blocking reactor, three-phase input blocking reactor that provides high impedance on the input to the filter. There's an output reactance on the same common core that compensates and reduces the voltage drops and improves performance. This combination of reactance allows us to design the filter with much lower capacitive reactive power, and there is a tuned branch circuit with the reactor and the capacitors. On the input, the filter is tuned below the fifth to prevent the importation of upstream harmonics. So the harmonics that we'll see in our power systems on a three-phase system, typically going to be fifth harmonic or higher. So by tuning below the fifth harmonic, we will prevent importation of these harmonics into the filter. And on the output side, it's tuned around the seventh harmonic to remove the harmonics generated by the load or the VFD. So a key design parameter is that we ensure that the capacitive reactive power is never greater than 15%. This is particularly at no load, where at higher loads the filter becomes inductive, but at lower loads the filter becomes slightly capacitive. So our capacitive reactive component, you can see at no load, never exceeds 15%. So here we have on the x-axis, on the left side, we're showing leading reactive power as a percentage of the full load rating of the filter, and on the right side we have lagging reactive power. And although we do introduce leading reactive power at these lighter loading conditions, it never goes above 15% of the total kVAR, or total kilowatt rating. Competitive filters are much higher levels, typically in the 35 to 40% range. And that's a problem because generators do not like to supply leading power factor loads. They're much better at supplying lagging power factor loads. And this graph shows a typical reactive power capability curve of a generator. In this case, we've got on the y-axis, we've got your load in kilowatts of the generator. On the x-axis, we've got the percent of reactive power leading on the left side, lagging on the right side. And there are the diagonal lines are the load power factor lines. And here, if we look at 0.9 load power factor at 80% load level, that would indicate a 40% reactive power component. So that's how we can read these charts that are provided by all generator manufacturers. For this generator, the envelope shows that at no load, reactive power must be less than 20%, but can be as high as 83% when the load is lagging or inductive. The Lineator AUHF reactive power consumption line is shown in green and is comfortably within the generator's capability envelope. The leading power factor of the filter is not a problem for the generator and is therefore unnecessary to switch out the capacitor under light loading conditions. The typical reactive power curve of most other filters is shown in red. At lighter loads, the capacitive reactance exceeds the acceptable levels of the generator and therefore likely to cause compatibility issues such as excitation control or regulatory problems. So misconception number 4 is that leading power factor is a problem for generators under any condition. Whereas in reality, although it is true that generators typically handle inductive loads better than capacitive loads, they are capable of handling a leading power factor load provided the capacitive reactance remains within the generator's reactive power capability curve. A harmonic filter with less than 15% maximum reactive power, capacitive reactive power, will meet this requirement. So the previous curve showed the capacitive reactive power. Well, the capacitive reactive power in combination with the inductive reactive power is going to result in power factor, the power factor as measured at the input to the filter. So these power factors, here we show the total power factor on the x-axis, again leading on the left from unity to 0, lagging on the right from unity to 0. And we can see that for our filter, from loading 30% and above, we are very close to unity and above 0.95 over that entire range. We do end up approaching a leading power factor, and that will drop off and go down to 0, because at no load, essentially what we have is just the capacitors of filters connected to the system. So we'll have 0 leading power factor. So the power factor can be low and leading with the filter under light loading conditions, but that's not a problem because the filter introduces very little voltage boost and it's compatible with the generators. It won't impact power factor penalties because remember we're lightly loaded when we go leading, and therefore there is no requirement to switch out the capacitors with a contactor. Other filters, of course, will remain leading until much heavier loads are reached and therefore can introduce problems to the generators. And one other thing that we discovered with our filter is that it helps protect the downstream load as a variable speed drive. Helps protect it against overvoltage transients and ringing that might be introduced by power factor switching transients by the utility when they switch out their power factor correction equipment. Or in this case, it was due to the rectifiers on the DC drives on a offshore drilling platform. So the graph on the left shows the voltage that was measured on the input of our filter. And we can see the overvoltage, the drop in voltage which is introduced by the rectifier, the overvoltage chute that we have with it, and then the ringing. And this, without the Lineator filter, the variable speed drive would see these overvoltage transients and will cause the drive to trip out, or in severe conditions will cause components to fail. On the drilling rig, the drives were tripping out on a regular basis. So on the input of the filter, in the output of the filter, supplying the variable speed drive, we've reduced the overvoltage peak, and we've filtered out the ringing to produce a much cleaner sine wave to the drive, and this will protect the drives. But if we switch out the capacitors under lightly loaded conditions, this protection no longer applies. You lose this added protection. So misconception number 5 is that harmonic filters must always be equipped with contactors to switch out capacitors under light loading conditions. Whereas in reality, a properly designed passive harmonic filter with less than 15% maximum capacitive reactance as a percent of kVA rating does not require a contactor to switch out capacitors at light loads. In fact, keeping the capacitors in the circuit can help protect the VSD from overvoltage transients. And that leads us to the final misconception, which is just simply that any leading power factor is bad. I can't tell you how many times that I've heard that from various engineers, consultants, or other customer engineers concerned about the fact that they're measuring a leading power factor. But in reality, there are many conditions under which a leading power factor will not cause problems, and they've been covered in this presentation. So in fact, if the other loads on the power system are inductive, introducing some capacitive reactance can be a good thing, as it can provide some compensation to improve overall power factor. So in summary then, we know now that harmonics are generated by nonlinear loads and have led to many power factor misconceptions. The reality is that low power factor is often caused by harmonic generating nonlinear loads rather than inductive loads. Power factor correction capacitors are not always the right solution for low power factor, and they can introduce system resonance issues. Power factor must be high during peak demand loading to prevent power factor penalties, but can be low at light loading conditions. And properly designed harmonic filters do not need capacitor switching contactors. Providing that reactive power remains within a generator's reactive power capability curve, it can handle a leading power factor load. And low leading power factor is not necessarily a bad thing, as long as the capacitive reactive power is kept low. So that completes our webinar today. I'd be happy to address any questions that may have arisen. So if you do want to post a question, you can do so through the chat console. Yeah, no, it's actually the question console, not the chat console. First question that's come up is whether we will be able to email the presentation to the attendees, and yes, that will be done automatically once the session is completed. You'll get a copy of the presentation, full copy of the presentation. Some other questions are asking if we've had any problems with applications involving generators and lineators. And actually, provided the total lineator load connected to the generator does not exceed the generator's full load rating, we have not had generator problems. There have been incidences where they've had a much higher connected load with all filters on it, and then we've gotten close to exceeding the generator's capability curves. But those are very rare, and certainly when it's properly loaded, it's never been a problem. There's a question about the fact that we mentioned that the filter protects the drive from transients, and they're asking for a little further explanation of that. This characteristic of our harmonic filter was actually discovered after we were asked to provide a solution on the drilling rig as described in the presentation. we wondered if the capacitors would help support the voltage during the commutation of the rectifiers, and also whether it would help filter out the ringing. And after we did some modeling, and we have a computer modeling software which is available for anybody. It's a free proprietary software that we have called Solve. And when we ran that simulation and looked at the and created a situation where we introduced a high overvoltage and ringing condition by adding capacitors in the system, when we applied the filter, we could see a substantial reduction on the output of the filter. So we were confident with that modeling that it would work, and sure enough, it worked in that application, and we've done many other applications since. Okay, let's see. We've got a question on how does the cost of linear compare to a 12-pulse or 18-pulse system. Typically, we see the combination of a lineator with a 6-pulse variable speed drive to being about 25 to 30% less expensive than a comparably sized 12-pulse or 18-pulse system when you include the transformer that's required for the phase shifting. There's another question here about voltage boost. It's asking if there's a problem with a voltage boost on the lineators. There is a slight voltage boost, but we make sure that it's between 2 to 3% maximum between the input and the output, and that occurs under no load conditions. This is typically not a problem for the variable speed drives. The only time it might be is if the maximum voltage rating of the drive is already being exceeded or approached. But this voltage boost is much less than what you would have with other competitive filters. Another question. Are these filters only applicable for one VFD on one load, or can they be applied to a medium voltage bus? Okay. The filters can be applied to multiple loads. They can be used on a single VFD load, or you can combine VFDs and size the filter appropriately for multiple VFDs. It is not presently available for medium voltage. The main reason for this is that you need to combine this filter with a 6-pulse drive in order to get the performance that we require, the reduction in harmonics. And there are no drive manufacturers today that provide a 6-pulse medium voltage drive, because they know that the harmonic content of a 6-pulse drive would create too much problems. And with a medium voltage drive, they're typically quite large drive systems, so they put some form of treatment, be it multi-pulse with phase shifting, an active filter, or some other form. It's a question about single-phase filters. We do have a model. It's our Lineator 1Q3, which is applied on applications where you've used a variable speed drive, where you only have single phase power available, which is typically 2 of the 3 phases. You have single phase power available. You need to connect up a 3-phase motor. They often use a variable speed drive that will accept the 2 phases in and produce 3 phases out to the motor. However, in that application, the drive needs to be dramatically oversized, and it will produce a lot higher harmonics. It'll introduce third harmonic in addition to the 5th and 7th. So our filter can be applied to this drive, where we'll take the 2 phases in and we'll supply 3 wires out to the drive. It's not a balanced 3-phase system, but it is better for the drive than a simple 2 phases, and will filter out the harmonics. It's a question about how the filter might cool itself. Our filters are convection cooled. There's no requirement for any mechanical cooling. And we install the capacitors in the intake air to keep the temperatures of the capacitors as low as possible. There's quite a few questions, so we'll go through as many as we can. How much better your harmonic filter compared to MTE, which claims to be the #1 in the industry? Our filter design is a very unique design. We've actually been #1 in the industry for quite some time now. We get the best performance with the lowest reactive power, the highest efficiency. So I would debate that claim of MTEs. Is there any others up there that... Still checking through. Is that one there? Okay. You indicated that harmonic content affects power factor. Am I correct that at light loads the harmonic is mathematically greater than the VFD, but has less demand distortion and therefore less of power factor impact? It is true that the percent THD will go up under lighter loading, but the actual harmonic currents in RMS value will be lower than they are when you're at higher loading levels. So the result is less of an impact on the power system, and it will the harmonic components will lower the power factor, but at lighter loads it's not as much of a problem on the system, the power system. There's a question: in a rural area where there are several installations of VFDs with filters and all the VFDs are off, would the capacitive reactance become an issue for the supply network? It's a good question. It really depends how many filters there are on the system, but typically the power system can handle some leading power factor, and if the power system is a quite stiff system, quite a fairly large system, or in rural areas sometimes they can be fairly weak systems, you'd need to look at the power system to determine whether that level of capacitive reactance is still suitable. But certainly as far as filters are concerned, the Lineator filter has the lowest capacitive reactance, so it is going to be the most suitable for that application. Yeah, I think there's a question about whether one filter can be used on multiple drives, and yes it can. It can be used on a single drive, or you can combine multiple drives and feed it from one filter. There is a series connected filter. Okay, I think we've got most of them. I hope that we have answered all the questions that everybody has. If an additional question comes up, please feel free to send an email to the Mirus address, mirus@mirusinternational.com, and we'll certainly address that for you and get you all the answers that you need. So I'd like to thank you very much, and I'll turn this over to Trish to close up.
Great. Thanks, Tony, and thanks everyone for your great questions. We hope this has been a helpful explanation of low power factor issues. As Tony mentioned, if you do have questions, don't hesitate to reach out to us, and we will be sending you an email with the link for the recording of today's webinar as well as the copy of the presentation. So if you have any details that you'd like to review or you want to share it with any of your colleagues. Thanks very much and have a great day.